Hello, in this video we will explain how to solve a problem from chapter 3 of the class Design of Experiments. The problem we are going to solve is problem 3.20. This problem describes several experiments investigating the rotting of concrete to removing trapped air. To better explain this process, we will show the next video.
Effective compaction enhances the strength and durability. In most of the RCC works, needle vibrators are used for compaction. Certain care is to be taken while using needle vibrator. The needle of the vibrator should be immersed vertically into concrete and should remain vertical throughout the operation.
As we saw in the video, the times that the rotting is put inside the concrete may or may not affect the resulting compressive strength of a concrete. To demonstrate how the compressive strength of concrete is tested, we will now see the next video.
The maximum load at which the specimen breaks is taken as the compressive load.
Once the experiment was conducted, the following values were obtained. On the left, we can see the rotting level, being 10, 15, 20, or 25 times. And on the right, we can see the compressive strength. Each row corresponds to a rotting level on the left. Solving this problem, we first must analyze the data observed. The first step is to get the sum of all rows. The second step would be to get the total of all sums. And the third step would be to get the average of each row. The data is as follows. The values from the table above, we can now pass to develop the ANOVA table. The ANOVA table consists of 4 columns: the sum of squares, the degrees of freedom, the mean square, and the F-test. To get the sum of squares, we must add the square of each row of the table above. The answer would be as follows. For the degrees of freedom, in the case of the rotting level, it would be the n minus 1, and in case of the total, it would be the total number of values minus 1. The error would be the difference of the total and the rotting level. The values would be as follows. The mean square is obtained by dividing the sum of squares by the degrees of freedom. The values would be as follows. Finally, the F-test is the division of the mean square of the rotting level divided by the mean square of the error. In order to get conclusions from this, we need to obtain the F value of 0.05 with x equals 3 and a. The answer would be 4.0661. The conclusion from this would be to accept the HO, given that the F-test is smaller than the F value. Taking this into consideration, we can assume that there is not a significant difference in compressive strength due to the rotting level. In other words, the rotting level does not affect the compressive strength. Be to obtain the residuals. These are obtained from the difference between the average of each row and the value of each cell. This table is arranged exactly the same way that the given values were. So in this case, the 30 of this table would also be from the left top cell of the original table. Following the same procedure, we can then obtain the other values. These first three values would correspond to a rotting level 10. The same way, we can continue until we obtain all of the values in the table. Once this is achieved, we must order the residuals from least to greatest. The first column represents the number of the residual. It's just a number going from 1 to the maximum of values we have. The second column is the residuals sorted from least to greatest. And the third column corresponds to a probability. The probability is assigned by subtracting 0.5 from the order and dividing it by the total number of residuals. For the first row, the answer would be 0.04. If we do this for the other 11 residuals, the answer would be as follows. Are used to make a graph. This graph represents the normality of the values. If the graph follows a pattern, or in other words, a straight line, then we can assume that there is no problem with the values. In this case, the points are aligned in a general line, so we can assume the values have no problems. Is the Duncan's test. With this test, we can verify the data obtained from the ANOVA table. In other words, we can see if we should really reject the HO, or in this case, accept it. The first step for performing the Duncan's test would be to get the averages, which we did in the first table, and sort them from greater to least. The order, represented by Y1 to Y4, represents their original order. Next, we need to obtain the standard error. After we obtained it, we must go to the R table and calculate it with x of 2, 3, and 4, and the other value of 8. If we go to that table, we will find that the values are as follows. After we've obtained the Duncan's R table, we must now obtain the minimum significant range. This is obtained by multiplying the standard error and the Duncan's R table. Those are the values. After we've obtained those, we must sort from the greatest Y minus the smallest one. After we've done that, we just proceed to making the difference, and the values would be the next. After we've gotten all those values, we must compare them with the reference value, which correspond to a minimum significant range. In order to know if each interaction is significant or not, we must compare the difference versus the reference. If the reference is larger than the difference, then we can assume that the levels are the same. And since in this test we see that the reference is always bigger than the difference, we can assume that all levels are the same and that our original hypothesis was correct.